Hello dear friends, welcome to my channel. Today's discussions is quantum field theory. So friends, you know already that free particles, okay, free field, and you know bosonic static field, you know a lot of topics I have already discussed, okay, in my previous quantum field video theorems. Okay, so now I want to discuss only interacting field theorems. The free field theories that we have discussed so far are very special. We can determine their spectrum, but nothing interesting that then happens. They have particle excitations, but these particles don't interact with each other. And here we will start to examine more complicated theories that include interactions term. This will take the form of higher terms in the Lagrangian. We will start by asking what kind of small perturbations we can add to the theory. For example, consider the Lagrangian for a real scalar field interactions field theory. Okay, L equals to half into del subscript mu phi and del superscript mu phi minus half m square phi square minus summation n less than equal greater than equals to 3 lambda n factorial phi to the power n. The coefficient of lambda n are called coupling constant. Okay, this is very important. You will already seen my short videos. I show coupling constant in my string theory field theory. Okay, so it is very familiar. I hope it is familiar to you in my channel that it coupling constant. What restriction do we have on lambda n to ensure the additional terms are small perturbations? We might think that we need simply make lambda n is very smaller than 1, but this is not quite right. To see why this is the case, let's do some dimensional analysis. Firstly, note that the action has dimensions of angular momentum or equivalent, the same dimensions as h bar. Since we have set h bar equals to 1 using the convention described in the introduction, we have box S equals to 0 and H is equal to d to the power 4x L, and d to the power 4x is equal to minus 4. The Lagrangian density must therefore have mod of L box of L equals to 4. So what does the meanings of this Lagrangian equation? Since box of del mu equals to 1, we can read of the mass dimension of all factors to find box of phi equals to 1, box of m equals to 1, and box of lambda n is equal to 4 minus n. And so we see why we can't simply say we need lambda n less than 1, because the statement only makes sense the dimensionless quantities, the various terms parameterized by lambda n fall into three different categories. Lambda n, box of lambda n equals to 1. For this term, dimensionless parameter is lambda 3 by E, where E has dimensions of mass. Typically in quantum field theory, E is the energy scale of the process of interest. This means that lambda 3 divided into phi cube divided by 3 factorial is a small perturbation at high energies. E greater than equals to lambda 3, more bigger than lambda 3, but a large perturbation at low energies E is the more less than lambda 3. terms that we add to Lagrangian with the behavior are called relevant because they are most relevant at low energies. In relativistic theory, E is greater than m, small m, and we can always make the perturbation small by taking lambda 3 more less than m. Okay, so box lambda 4 equals to 0. This term is small. If lambda 4 is more less than 1, such perturbations are called marginal, and lambda n less than 0 for n greater than equals to 5. The dimension parameter is lambda n e to the power n minus 4, which is small at low energies and large at high energies. See, such perturbations are called irrelevant. As you will see later, it, it is typically impossible to avoid high energy process in quantum field theory. So let me note, okay, we have already seen glimpse of this computing the vacuum energy. This means that but in vacuum energy you get my fourth quantum field theory. I have already created vacuum energy. Okay, this means that we might expect problems with irrelevant operators. Indeed, this lead to non-renormalized field theories in which one cannot make sense of the infinities at arbitrarily high energies. This does not necessarily mean that the theory is useless, just that it is incomplete at some energy scale. Let me note, however, that the naive assignment of relevant and marginal and irrelevant is not always fixed in stone. One term corrections can sometimes change the character of an operator. An important aside, why quantum field theory is simple. Typically, in a quantum field theory, only the relevant and marginal couplings are important. This is basically because, as we have seen above, the irrelevant coupling become small at low energy. This is huge help of the infinite number of interaction terms that we could write down. Only handful only a handful are actually needed, just two in the case of the real scalar field described above. Let's look at the little more. Suppose that we someday cover the true super duper theory of the everything unimportant. Theory of everything unimportant that describes the world, okay, that describes the world at very high energy scale, say GUT scale or Planck scale, whatever the scale, let's call as a capital lambda. Box of lambda means energy scale. It is an energy scale. Box of lambda is equal to 1. Now we want to understand the lower physics down at our Puni energy scale. E less than more less than more less lambda is the more bigger than E. Let's further suppose that down at the energy scale E, the laws of physical of described by real scalar field, they described by non-abelian gauge field and fermions, but the same arguments applies in the case. So bear with us. The scalar field will have more complicated interaction terms, where the precise form detected by all stuff that's going on the high energy super duper theory. What are these interactions? Well, we could write our dimension full coupling lambda n in terms of dimensionless coupling gn and multiplied by a suitable power of the relevant scale capital lambda. The exact value of the dimension coupling gn depends on the details. Higher energy, okay, please read. Okay, higher energy super duper theory, but typically one expects them to be a order gn proportional to o1, means that the experiments means at small energy E is the more less than capital lambda. The interaction terms of the form phi to the power n with n greater than 4 will be suppressed by powers of E divided by capital lambda to the power n minus 4. This is usually suppression by many orders of magnitude. Okay, it is the simple argument based on dimensional analysis that ensures that we need only focus on the first few terms in the interactions, those which are relevant and marginals. It also means that only if we only have across to low energy experiments, it is going to be very difficult to figure out high energy theory because its effects are highly diluted except the irrelevant and marginal interactions. The discussion given above is a poor man's versions of the ideas of effective field theory and Wilson normalization group, about which you can learn more in the statistical field theory course. Examples of weakly coupled theories. In this course, we will study only weakly coupled theories, ones that can truly be considered as a small perturbations of the free field theory at all energies. In these sections, two type of interactions. One is phi to the power 4 theory. That equations is Lagrangian. Please check this Lagrangian equation with lambda is the less than 1. We can a hint for what the effects of the extra term will be expanding out phi to the power 4 in terms of a subscript p capital P vectors and a plus subscript p vectors. We assume some interactions that look like this etc. This will create the destroy particles. This the suggest that the phi to the power 4 Lagrangian describes a theory in which particle numbers is not conserved. Indeed, we can check that the number operator n capital N now satisfies Poisson does not equals to 0, Poisson h comma n and Poisson, okay, Poisson, okay, scalar Yuka theory. Yuka theory. So Lagrangian is this equations. Please write down Lagrangian equation, and with G less than M comma capital M comma capital N, this theory couple complex scalar psi to real scalar phi, while the individual particular number psi and phi are no longer conserved. We do still have the asymmetric rotating the phase of psi and ensuring the existence the charge q defined q Poisson QH equals to 0. This means that number of psi particles minus in the number of psi antiparticles is conserved. It is common practice to denote the antiparticle as psi bar. The scalar yoga theory has a slightly worrying aspect. The potential has a stable local minimum at phi equals to psi equals to 0, but unbounded below of large enough minus. So this is, so friends, we see that that the potential has a stable local minimum at phi equals to psi equals to 0, but is unbounded below for large enough minus g phi. This means we should not try to push this theory too far. A comment strongly coupled field theories. In this course, we restrict attention to weakly coupled field theories, where we can use perturbative techniques. The, the study of strongly coupled field theories is much more difficult and one of the major research areas in theoretical physics. For example, some of the amazing things that can happen include charge factorizations, charge fractionalizations. Okay, although the electrons have electric charge 1, under the right condition, the elementary excitations in solid have fractional charge 1 by n, where n belongs to 2z plus 1. For example, that occurs in the fractional quantum Hall effect. Okay, fractional quantum Hall effect. Okay, confinement. The elementary excitations of quantum chromodynamics QCD are quarks, but they never appear on their own, only in groups of these in a baryon or with antiquark. They are confined. Antiquark is in a meson. Okay, so emergent space. There is there are a field theories in four dimension which at strong couple become quantum term gravity theories in 10 dimensions. The strong coupling effect causes the excitations to act as if they are gravitons moving in higher dimensions. This quite extraordinary and still poorly understood. It's called the ADS and CFT correspondence. So friends, ADS or CFT, you can get quantum gravity videos in my channel. I have already discussed what is ADS and CFT and gravitons. Okay, so let's go the interactions pictures. Interactions pictures, there is a useful viewpoint in a quantum mechanics to describe situations where we have small perturbation to well understood Hamiltonian. Let's return to the familiar ground of quantum mechanics with a finite number of degrees of freedom. For a moment in the Schrodinger picture, the state evolve as I into d. These equations we get Schrodinger equations. this is the Schrodinger equations. Okay, so H for Hamiltonian. The while the operator OS independent of time. In contrast, in the Heisenberg pictures, the states are fixed and operators change in time. OHT, this is the equations, and the interactions pictures is a hybrid of the two. We split the Hamiltonian up as a H equal to H0 plus H int. The time dependence operators is governed by H0, while the time dependence states governed by H int, means H interior. Okay, so interactions. Okay, H interactions, although the split into H0 and H int is arbitrary, it is useful. H0 is soluble when H0 is Hamiltonian for a free field theory. The states operates of the interactions pictures will be denoted subscript I and are given by these two equations. The last equations also applies to H int, which is time dependent. The interactions Hamiltonian in the interactions picture. So H int is interactions Hamiltonian. Okay, and H0 is Hamiltonian for a free field theory. Okay, so must remember H0 is Hamiltonian for free field theory, and H int is the Hamiltonian interactions pictures, because you have already studied Heisenberg's pictures. The Schrodinger, okay, the interactions of the Hamiltonian, okay, you get these equations. Okay, the Schrodinger equations for states in the interactions picture can be derived starting from the Schrodinger pictures. Okay, this is the Schrodinger pictures, and we get this, and so we learn these equations. Now we discuss Dyson's formula. Well, Brimham has matched the best theoretical physicist to work with. The Peerless Beeston's has matched the best experimental physicist. Powell and Cambridge has some excellent architectures. You can make your choice. Oppenheimer advised to Dyson's on which university positions to accept. You want to solve, let's write solution as this equations. Okay, and where ut comma t0 is a unitary time evolution operator, and such that ut1 ut2 is equal to ut1 t3 and utt is equal to 1, the then interactions picture Schrodinger equations requires I into du by dt h1t into u and hit I. Okay, if hi are a functions, and then we could simply solve these equations. Their problem, our Hamiltonian h I is an operator, h subscript I. Okay, we have ordering issues. Let's see why the case says trouble. The exponential of an operator is defined in terms of the exponential operators. Okay, we get these equations, but when we try to differentiate this with respect to t, we find that the quadratic form gives us these equations. Okay, so claim that the solutions is given by Dyson formula out of by Dirac, although e computation notation is due to Dyson. This is the Dyson's formula, and T stands for time ordering ring where operation evaluated at later are placed to the left. This is the total. Okay, expanding out the expression, we now have this value we get. And actually this last two term to double up since these equations, okay, that the range of integration is the first expression is over t double dash and t dash, okay. Okay, in the second expression t dash dash dash, okay, t dash, this equation, these conditions, which is of course something, the final expression is the same second expressions, some simple relabeling. This means that we can write these equations ut comma t zeros. And now proof of the Dyson's theorems. Dyson's theorems, Dyson's formula is simpler than explaining what all the notations means. First, observe that under the t sign all operators commute, and thus we get these equations. And since t being the upper limit of the integral is the last time h subscript I t can be pulled out to the left. Before moving on Dyson formula is rather formal. It is typically very hard to compute time ordered exponential in practice. The power of the formula comes from the expansion, which is valid when h subscript I is small and is. So friends, you see the proof of the Dyson's formula. Okay, now a first look at scattering. Let us now apply the interactions picture to field theory, starting with the interaction Hamiltonian for our scalar Euclid theory. H interior means internal, okay, internal field, internal Hamilton. I have already discussed that H means internal Hamiltonian. So H in internal Hamiltonian equals to G into d cube x psi plus psi phi. Unlike the free theories discuss the interactions does not conserve particle number, allowing particles of one type to morph into others. To see why this is, we use the interactions pictures and follow the evolutions of the state. Ket psi t is equal to ut comma t0 ket psi t0, where ut comma t0 is given by Dyson formula, which is an expansion to in powers of h internal Hamiltonian of internal. But Hamiltonian of internal contains creation and any annihilation operators for each type of particle in particular. So phi such that a plus a plus means a conjugate. This operator can create the destroy phi particles. Let's call them mesons. And psi is equal to b plus c conjugate. The operator can destroy psi particles through b and create anti particles through c plus. Let's call these particle nucleons. Of course, in reality, molecules are spin half particles and don't use from quantization of a scalar field, but we will treat our scalar Yukawa theory, okay, so as a toy model for nucleons interacting with mesons, okay. So psi conjugate is proportional to b conjugate plus c. The operator can create nucleons through B conjugate and destroy anti-nucleons through C. Importantly, Q is equal to Ne plus Nb remains conserved in the presence of Hamiltonian internal Hamiltonian. At first order in perturbation theory we find the term Hamiltonian internal like C plus C conjugate B plus A. This kills a meson, producing a nucleon antinucleon pair. It will contribute to meson decay. Phi tends to psi into psi plus. At second order perturbation theory, we will have more complicated terms in each in internal Hamiltonian whole square. For example, C conjugate into B conjugate into A conjugate first bracket and first bracket C B A conjugate. This term will give contributions to scattering process psi and psi conjugate phi tends to psi conjugate. The rest of this section is devoted to computing the quantum amplitude for this process to occur. To calculate amplitude, we make an important and slightly and dodgy assumptions in initial and final states are eigenstates of the free theory. This means we take the initial state ket I at t tends to minus infinity, final state ket f at t tends to plus infinity to be eigenstates states of the free Hamiltonian H0 at some level. The sounds plausible at t tends to minus infinity. The particles in scattering process are far separated and don't feel the effect of each other. Furthermore, we intuitively expect the states to be eigenstates of the individual number operators in which commute with each subscript 0 but not each int, means each subscript int. As the particles approach each other the interact brief before departing, again each going on its own merry way. The amplitude to go ket I and ket to ket f is limit t plus minus tends to infinity plus minus infinity, these equations. Okay, here the unitary operator S is known as the S matrix. S is for scattering. There are a number of reasons why the assumptions of non-interacting initial and final states is shaky. Obviously, we cannot cope with bound states. For example, the formalisms can't describe the scattering can't describe the scattering of an electron and proton which collide and bind and leave as a hydrogen atom. It's possible to circumvent the objections since it turns out the bound state show as poles in the S matrix. More importantly, a single particle a long way from its neighbors is never alone in the field theory. This is true even in classical electrodynamics, where the electron sources the electromagnetic field from which it can never escape. In quantum electrodynamics, a QED, a dilated phase, is that there is a cloud virtual photons surrounding the electron. This line of thought gets us into a issues renormalizations mode on more on the next term AQFT course. Nevertheless, motivated by the problem, after developing scattering theory using the assumptions of non-interacting asymptotic states, meson decay. Consider the relativistic normalized initial and final states. Okay, ket I is equal to this and ket f values. The initial state contains a single meson of momentum p, and the final state contains nucleon antinucleon pair of momentum qi and q2, and we may compute the amplitude for the decay of a meson to nucleon antinucleon pair to leading order in G. It is these equations, and let's go slowly. We first expand out phi such that phi proportional to a plus, and remember that the phi in this formula is in interactions pictures, which is the same as Heisenberg pictures of the free theory. The a piece will turn and ket I into something proportional to ket 0, and while the a conjugate piece will turn into ket I into two meson state, but the two meson state will have zero overlap with ket bra f. There is nothing to psi conjugate operators that lie between them to change this fact. So we have these equations. We get these equations. Okay. Next, where in the second line we have computed ak and passed conjugate ap and picking up the del cube into p minus k delta functions which kills the d cube k integrals. We now similarly expand out psi proportional to b plus c conjugate and psi plus proportional to b conjugate plus c to get non-zero overlap with ket f. Only b conjugate and c conjugate contribute for they create contribute for they create the nucleons and antinucleus from ket 0. We get okay, we get if okay if si with that equations we get okay our quantum field theory amplitude. We get our first quantum theory field amplitude. Now we discuss recovering the propagator. Okay, recovering propagator, we know that phi x is equal to phi plus phi minus x. Phi plus x also we know d cube pi p into 2p whole cube 1 by root over 2 ap minus e to the power I minus ipx. Okay, phi minus x also value we know that equals to d cube p integration d cube p 2 pi whole cube and 1 by root over 2 ep a plus a conjugate p and e to the power plus ipx. Okay, where the signs phi plus minus makes little sense. And phi proportional to e to the power IEET, and which is sometimes called the positive frequency piece, and while phi minus e to the power plus IEET the negative frequency piece, and then choosing x0 greater than 0, and we get a mapping t phi x phi y is equal to these equations, and we get Feynman propagator get phi x Poisson bracket phi plus and phi minus x. Okay, where the last line normal order on for our troubles, we have picked up the extra term dx minus 1 is equal to 5 plus 5 minus x. So I get these equations should be can be written this way: t phi x phi y and phi y plus d x minus y. Meanwhile, for y0 greater than x0, we may repeat the calculation to find t phi x phi y is equal to these equations. And so putting this together, we have the final expressions, these equations. Okay, del f is equal to Feynman propagator defined the in which the del f xy these equations. Definitions. We define the contractions of pair fields of the string operators. Okay, recovering propagator we discuss. So the definition: string operators phi x1 phi x2 to mean replacing those operators with Feynman propagator, leaving all other operators untouched. We use the notation this phi x1 phi x2 and to denote the contraction. So for these equations we get, okay, a similar discussions holds the complex scalar fields. We get these equations the prompting us the define the contractions. Okay, now we discuss weak theorem for any collections of the phi 1 is equal to phi 1 and this phi 1 is equal to phi x1 phi 2 phi x2. So you get possible contractions. So to see what the last part of the equations means, let's look at an example for n equals to 4. Friends, let's discuss Weak's theory. So Weak's theory, I have already discussed that for any collection of fields phi 1 is equal to phi x1 and mapping, you see, and another factors you see that to see what the last part of the equations means, let's the example n equals to 4, then we get four similar terms. Okay, so now let's prove this theorem. The proof of this theorem that Weak's theorem. The proof of Weak's theorem proceeds by inductions. A little thought. It's true for n equals to 2. Suppose it is true phi 2 phi n. This is we will get this, and then we can pull phi 1 out of the left of the order of the product writing, and t phi 1 is equal to this is the contractions, and phi 1 minus term stays where it is, since it is already normal ordered in to write the right side of the normal ordered product phi 1 plus. So del phi k is equal to del f into x1 minus xk. So this is the proof of the contractions. Now example is nucleon scattering. Let's look that we have initial and final states ket I and ket f is equal to ket p1 comma p2 p1 dash p2 dash ket values. So we can then look and at the expansion of expectations if si. In fact, you really want to calculate expectations if s minus 1 I, since we are not interested in situations where no scattering occurs. As order d squares, we have the term ig whole square. This is equations. Now using weak theorem, we see there is a piece or in the string of operators which looks like these equations and which will contribute to scattering, because the two psi fields annihilate the psi particles, while the two psi plus fields create psi particles, and any other way ordering the psi and psi plus fields will give zero contributions. This means that we have this equation, this large equations we have, where in going to the third line we have used the fact the relativistically normalized state e to the power ipx. Now let's insert this into the expressions fsi. So we get these equations, and where the expressions in square brackets, while the final integral is the phi propagator gator, which comes from the contractions. Now x1 equivalent equivalent to x2 terms double up with the other to cancel the factor half out front. Meanwhile, the x1 and x2 integrals give delta functions. We are left with the expressions. Finally, we can get this. We can trivially do the d to the power 4k integral using the delta functions to get this value. Momentum conservations p1 and p1 dash, and this ensures that the momentum of the mesons is equal to k0 comma p minus p dash. We therefore have the end result I into ig whole square. Okay, result we get, okay, del to the power 4. Okay, previous result we get. Now another example is meson nucleon scattering. If we want to compute psi phi and psi to tends to psi phi scattering at other g squares, we would need to pick out the term psi plus x1 phi x1 psi x2 phi x2, and this is the, and similar term with the psi and psi plus exchanged once more. The term also contributes to similar scattering processes including psi phi and psi conjugate psi phi and phi phi and psi psi. So friends, phi phi tends to psi psi. So friends, this is my last lectures. I hope that I create a long lectures, but next videos is Feynman diagrams. Okay, so Feynman diagrams, I have already created a short video, but for short video is not so much good for understanding. So I will discuss Feynman diagram, Feynman rules, examples of scattering amplitude, and Mendel's stem variable, the Eucas potential, 5 to the power 4 theory, connected diagrams, amplitude diagrams. So this interesting portion, decay rates and Fermi golden rules, okay, cross sections, Green's functions, and connected diagrams, and vacuum bubbles, and Green functions to S matrix, and the Dirac equations, okay, and quantizing the Dirac field and quantum electrodynamics. And after that, this course will these sessions will be complete. So please keep watch, and I hope that I give better and best information to you.